This video is about triangle wave oscillators. It corresponds to section 36.2 of Applied Analog Electronics. We've seen an oscillator once before. We saw a hysteresis oscillator, which consisted of an inverting Schmitt trigger, a feedback resistor, and a capacitor. And if we looked at the voltage on the capacitor, what we got was that when the output was high, we would get the capacitor charging, RC charging constants, until we reached the high voltage, the high threshold of the Schmitt trigger. Then, because this is an inverting Schmitt trigger, its output would go low, and that would start discharging that capacitor through the resistor, and we would get an RC discharge until we got down to the low threshold. Once we got down to the low threshold, then the output of the Schmitt trigger goes high and it starts charging again. So this looks very much like a triangle wave, except for one problem. We have these shark fin shapes. And for a triangle wave, we really want to have a nice straight line there and a nice straight line there. The problem is that RC charging, the voltage across the resistor changes as the voltage on the capacitor changes, and so we get a charging current that varies. What we want is something where the capacitor charges at a constant rate. We have a constant current driving the capacitor. Well, we see a circuit for doing that. If we take an integrator, all right, and we have an input here which is either high or low, then we'll end up, if this is high, we'll end up with the voltage dropping at the output, and if it's low, we'll end up with the voltage rising at the output. So if we take that rising or falling voltage and run it through a Schmitt trigger, now this time a non-inverting Schmitt trigger. So over here we had an inverting Schmitt trigger, here we've got a non-inverting one. That's because we've got inversion going on in this integrator. We've got a constantly falling slope here. When we get down to the low threshold of this, then this is going to switch the output to being low, and then when the output's low, we'll have a constantly rising voltage here until we get to the high threshold. And so we're going to end up with a waveform that goes up, down, down. And if this is running between 0 and VDD for the low and high, if this integrator is centered at VDD over 2, then we will have the same slope negated for the two parts of the waveform here, and we'll have a nice symmetric triangle wave. So that's the basic idea for a triangle wave oscillator, is that we replace this RC charging concept here with the integrator. Let's take a look at that schematic in a little bit more detail. Okay, so what have we got? Down here on the bottom, that is just VREF, VDD over 2. We've got two identical resistors there, capacitors to keep any noise out, and we don't need a unity gain buffer or anything here because this is only going into the inputs of op amps, and so no current is needed. Up in the upper left corner here, we have our integrator. The RC time constant of the integrator determines what the slope is going to be, because the input to the integrator, coming in over here on the left, is going to either be 0 or VDD. We've got our centered voltage is VDD over 2 for the reference voltage for the integrator, so it's either going to be VDD over 2 divided by RC, or minus VDD over 2 divided by RC as the slope of the output. So the RC time constant determines the slope of the voltage. And the triangle wave output is coming out directly as the output of the integrator. And this last circuit here is a non-inverting Schmitt trigger. And the two resistors there determine what the thresholds are for the Schmitt trigger. And again, because our reference voltage coming on the negative input of that op-amp is VDD over 2, our two thresholds are going to be symmetric about VDD over 2. And we can take a look at what those are. Let's switch back to paper here and do a little computation with that, what that 10K and 40K resistors will be. So we have got, let's take a look at what happens if we've got the output being low. So there we've got a 40K resistor to ground being the output of the op-amp. We've got the center point here. That center point has got to is going to make a transition when it hits VDD over 2. And then this is the triangle wave here. So question is, when what voltage does this triangle wave reach VDD over 2 on the voltage divider? And that's just voltage divider equation. VDD over 2 is 40K over 40K plus 10K times V triangle, or the V triangle is equal to, this would be 4/5, so that'd be 5/8 VDD. And that's the high threshold. If we go through the same math but put VDD on the bottom here, we would get that V tri is 3/8 VDD. So this is V high and this is V low. So that's 3/8. Obviously, you can look at the schematic. You can change the R2 and R3 here to change what the two thresholds are, so what the range of the voltage swing is. And you can change R1 and C1 to change the time constant to get you the slope. And between those pair of parameters, you can control the period of the triangle wave oscillator. And that's really all you really need to do a fixed frequency triangle wave oscillator, is set the thresholds with the Schmitt trigger and set the slope with the integrator.